Hey everybody, I am Scott Bednar.
And I'm Jessie Wild.
And we are very excited to bring you live coverage from NASA's Moon to Mars Ice and Prospecting Challenge. We are coming to you live from NASA Langley Research Center inside their historic aircraft hangar.
You're probably wondering what's going on behind us. Well, teams have gathered in from around the country, and they are testing their own drilling systems. These teams are attempting to solve a lunar and Martian exploration challenge, and that is how to extract ice, subsurface ice, and melt that ice into water.
This is not something that's simple to do, but these teams seem to be up to the task. So why don't we get a closer look at what's going on behind us?
Let's do it.
So we've recently discovered what are thought to be large ice deposits under both the lunar and Martian surfaces. So these ice deposits could play a very significant role in establishing a sustained human presence beyond our planet. I mean, imagine if you went to the moon and you could actually harvest the water and use it for drinking or for propulsion or for other resources. The farther that humans venture into space, the more important it becomes to manufacture materials and products using local resources.
That's absolutely right, and that's actually called in situ resource utilization. We're going to get to that a little bit later in the show. NASA is preparing to send the first woman and the next man to the moon in 2024. With new technologies and systems, we're going to be able to explore more locations across the surface than we ever thought was possible. And this time when we go, we're going to establish a sustainable human presence on and around the moon.
What you're going to see today at the Moon to Mars Ice and Prospecting Challenge represents an important step in human exploration of the moon.
I hope you stay with us today as we tour how each of these teams has approached the challenge of harvesting water ice from beneath a simulated slice of extraterrestrial worlds.
Okay, Jessie, I am very excited to dive right into this challenge. In fact, I think we should show everybody at home one of these ice drilling systems and get a better close-up view. And maybe get a better idea for just how the Moon to Mars Ice and Prospecting Challenge actually works.
Let's do it.
So let's take a look at one of these big blue bins. You are going to see a lot of these today, and that's because every team has one. What's inside? Well, there are layers and layers and layers of unknown materials that's unknown to the teams. Ultimately, what they need to do is figure out a way to get through all of those layers and reach a giant ice block beneath. Once they get to that ice block, then they need to figure out how to extract it, how to harvest it, and bring it up to the surface as liquid water. If everything goes to plan, that liquid water will begin to pool inside one of these beautiful buckets. Later on, judges are going to assign point values to the team based on things like how much water they were able to collect and how clear the water is. Is it something you would want to drink? Yeah? Well, then you get more points.
But before they even reach that ice, they have another challenge ahead of them. These teams actually have to dig through several layers of what's meant to be the simulated surface of the Mars and Moon. They don't know what the layers are made of, they don't know how many layers there are, how thick they are. So that's something that they have to determine using drilling telemetry. So they're actually collecting data on the drill that you see here, and they're putting that together into a digital core. That's basically a demonstration of their knowledge and understanding of those layers, and they're going to be judged on that as well.
Yeah, they're going to be going.
Now, before we go more into depth with the teams and their technologies, I'm going to throw it back over to Scott, and he's going to talk a little bit about the Moon to Mars Ice and Prospecting Challenge. Over to you, Scott.
Douglas is NASA's Chief Technologist. Thank you so much for joining us.
Hey, it's great to be here. I'm really excited about being a part of this.
So I've got to ask first, what does a Chief Technologist do?
Yeah, great question. So the Chief Technologist role is to really advise the administrator and the leadership team on technology policy, and to help to shape and guide our technology investment strategy across the 4 mission directorates across the agency.
Oh, fantastic. So I also understand that NASA is embarking on some very exciting plans to return to the moon. Please tell me more about that.
Yeah, so we've got Project Artemis, which is our effort to return the first and to land the first woman on the moon by 2024. It's like one of the most exciting times in NASA's history. We've got a series of activities that are ongoing now already with the SLS, Orion, the Gateway, and we're planning to build landers using a lot of commercial partners and international partners eventually to do what's going to be an exciting, not just return to the moon, but to develop the moon's resources and for long duration sustainable activity on the moon.
We want to stay there this time.
That's right.
So what are challenges like the Moon to Mars Ice Prospecting Challenge add to that? How do they add to our journey to the moon?
Yeah, so the difference between what we really need for long missions in space, whether it's the moon or Mars eventually, is really to be able to use the resources that are there, right? It's just too incredibly expensive, both from a cost and mass standpoint, to bring everything with us. We can kind of do that for a sortie, a short duration stay like they did on Apollo, but if you're going to be there for an extended period, really live and work like we do on the International Space Station, we absolutely need to learn how to use all the resources that are in situ, on the surface, there at the moon and in the environment. And this challenge is exactly targeting one of the key resources that we're trying to exploit on the moon.
Which would be water.
Which would be water in this case.
So what do we know about water on the moon or even on Mars?
Yeah, so what's really interesting is if we were having this conversation even 5-10 years ago, that would be there'd be a lot of speculation. But recently with our robotic efforts, we can now confirm that there's billions of gallons of water on the South Pole, North Pole of the moon. There's water on Mars, in the regolith on Mars, and we're learning now with efforts like this how we can extract and utilize that resource.
So the things that these students are doing today, the demonstrations, the technological demonstrations they're showing us, could actually have a direct impact on our future exploration of the moon.
Absolutely. And I have to say, as I walked around and looked at some of these, the setup is pretty realistic, pretty representative of what we'd expect in terms of the conditions and the regolith and so on. And I'm just impressed by the variety of approaches that are being taken.
It's very exciting for students to have this opportunity as well. What does NASA get out of engaging students in university at this age?
Yeah, so great question. I mean, I think we all recognize that myself and my generation many of us were inspired to STEM and science and math and technology careers from what we saw. And what we're doing now with Artemis and our moon and going on to Mars is inspiring another generation. But that's a two-way street because we're providing inspiration to students, but at the same time, we're getting really diverse new ideas, different approaches from our university partners, from student teams that we wouldn't get otherwise.
That's fantastic. It's a different way of thinking.
It is a different way of thinking. And I think that's kind of the hallmark of innovation, right? It's kind of a diverse, different point of view with a different set of experiences.
That's fantastic. Well, Douglas, I want to say thank you very much. I hope you enjoy the rest of the Moon to Mars Ice and Prospecting Challenge.
Awesome. Thanks for having me.
All right, Jesse, I'm going to throw it back to you.
Thanks, Scott. For those of you just joining in, we are live from NASA's Moon to Mars Ice and Prospecting Challenge, where university teams are drilling through simulated lunar and Martian soil in an attempt to extract the ice below. One day, systems like these could be used to extract water below the surface of the Moon or Mars. And for future explorers, accessing water will be crucial for creating a sustained human presence beyond Earth. Let's go talk to one of the teams. We're going to talk to Virginia Tech first. Maria, thank you so much for being with us.
Yes, thank you.
So tell me a little bit about your design.
So our design is the overburden layer ice to vapor extracting robot. Originally intended to heat up the ice and then we would extract vapor. Now for on-Earth operation, we do have to extract water instead of vapor, just because of the atmosphere on Earth that would be absent on the Moon or Mars.
And do you know how your system compares with some of the other teams here?
So I think what really separates Oliver from the rest is that it's part of a bigger picture. So our lab, the Field and Space Experimental Robotics Laboratory, does a lot of work with in-space assembly and in-situ resource utilization. So for us, Oliver is just another tool in making sure that humans become a multi-planet civilization.
That's really awesome. And how is everything going for you today?
It's going pretty well. We're actually about to start up again on hands-on operation.
And what does that mean, hands-on operation?
It means that we'll be in full control of the robot, and later on we may choose to go autonomous, meaning that Oliver will be behaving by itself.
Do you expect that you'll be able to go autonomous?
I think we will be able to, yes.
And are you expecting to be able to collect some water?
I think we will. I'm fairly confident, yes.
Awesome. Thank you so much for talking with me, and good luck to you. I'm going to throw it back over to Scott, and he's going to talk to another one of the teams.
Thanks, Jesse. All right, I want to introduce everybody to Team West Virginia and my friend over here named Kermit. Kermit, good to see you again.
That's probably good.
So you have got a very interesting solution to get down into this and drill. Tell me a bit about it.
So our theme this year was to keep things as simple as possible. So we're using only one bit to penetrate the overburden and extract water. You can see here, this is our all-in-one probe, the AIOP, which drills down into the overburden and then melts the ice. This was designed by us with the hard overburden layers in mind, and it was manufactured and fabricated by Protolabs, a professional prototyping company based in Minneapolis. So it includes a PDC bit that can go through any hard layer, a copper heater housing that houses all the heaters that melt the ice, and a aluminum body, and a slip ring and a water swivel that allow the drill to rotate. And our rig itself is made out of carbon fiber to decrease weight, and we also have a really cool filtration system that uses electrocoagulation to clear out debris from the water we'll extract.
Okay, you've really got this solved. So how is it working so far? Have you gotten through the different layers?
So we've gotten through the different layers, and right now we had a problem with our first AIOP. It got clogged. We unclogged it, and right now we're trying again to extract the water. We should have water in a couple of minutes now, we're hoping. So we're going to do that and move to another area to drill, hopefully soon.
Okay, well, I wish you the best of luck, and good luck finding that water. I hope you hit a spring. So thank you very much. All right, let's go check back in with Jessie, who's out on the competition floor, and see what she's up to. Jessie, back to you.
As we walk around the pit today, you're going to see that all of these drilling systems have a unique design. Each team brings a different idea to the table, and that diversity of ideas that we get from including students in a competition like this really helps our collective understanding. Now, today is day one of the competition, and teams are operating their systems for the very first time.
That's right, and it's actually very exciting how unique these different systems are. Most of the university students today are using a drill to dig through the simulated lunar and Martian soil to get to that ice below it. Along the way to that ice, these teams must collect data about the layers that they're drilling through. How many layers are there? How thick are they? How dense are they? And then they will use this information to create a digital core that they will be judged on later in the competition. Okay, I think Jessie is actually with one of the competition organizers, so let's go check back in with her and learn a little bit more about how this competition came to be. Jessie, back to you.
Thanks, Scott. I'm here with Shelly Spears, who actually is in charge of putting this whole event together. So Shelly, thank you for being with us. And can you tell me a little bit about how the competition is going today?
Competition is going beautifully, especially considering that we added a level of rigor and difficulty to this year's competition. We're thrilled with the progress the teams are making, and I know they're thrilled as well.
And tell me about that level of difficulty. What did you add this year? I understand the teams actually have to collect data.
They do. So we added a prospecting element. So what we mean by that is that the teams, as they go through the overburden on their way to the ice, and the goal is to harvest ice, but there are multiple layers that have been placed inside this overburden that we very carefully packed earlier this week. And so we're asking the teams to use drilling telemetry to provide a little bit of ground truth about what the characteristics are of the overburden as they make their way to the ice.
And why is it important for them to be able to do something like that?
Well, we really need them to provide, like I said, this ground truth of understanding exactly what those layers are like as opposed to guessing. So I think that kind of data will help inform how we perhaps engineer our instruments and how we can use that data to better understand really what's going on below the surface.
That's a really neat addition to the challenge. It seems like it also would be very difficult. Do you know how the teams are doing so far?
I think they're doing pretty well. We've had a couple of teams who've already gone through the process of creating a digital core. Some of them are going to wait until tomorrow to go through that process. And they're going to be looking at things like their penetration rate, the power, and then also some of the speed, some of the information. So it's fairly simple data that they're going to be collecting, but it's very useful data. And I think that it's going to help really inform some of what NASA's doing when they're looking at drilling on the Moon and Mars.
And why is it so important to have challenges like this?
I think these challenges provide a relatively low-cost opportunity for NASA to be able to explore the trade spaces and concepts and designs for this really important ISRU challenge of harvesting water. It's really one of the most important challenges that we face in space exploration. So they're able to actually see what these prototypes look like and how they operate, and sometimes just seeing is believing. I mean, there's nothing, you can write a paper about it, but when you actually see it working, there's no substitute.
And it's been really cool to see all of the designs here today. I know there's also a big industry component. Can you tell me a little bit about that?
Sure. We've been so lucky to have our industry support with Honeybee Robotics. They've been terrific, providing judges. We have SpaceX. We have Dr. Keith Nicewarner, who's with us who heads up Mars Surface Robotics for SpaceX. These companies have been really helpful in helping inform the requirements and constraints and the design of the competition. And we also have sponsors that are helping us with turbidity testing, which is looking at the clarity of the water and the quality of the water that they're harvesting, as well as companies like Aerocon and Buccal Stone that have provided some of the materials that are in the overburden that leads to this prospecting element that we added this year. So really thank them so much for all their support. And one last thing is with Protolabs, they provided $20,000 in service grants for some of our teams to apply for grants for them to be able to do rapid 3D manufacturing. So really appreciate all of their help.
That is awesome, and I think we're actually going to see some of the parts that were printed.
Yes.
Throughout the show. And for students watching at home, how can they get involved in future competitions?
Well, for this particular competition, we're already working on the design for the competition for next year, and we expect to release it probably in July or August. And it'll go out to the university community, and they're welcome to check back on their website, which I know you have published on the feed, and check back in July or August.
Wonderful. Well, thank you so much, Shelly. I know you're very busy, so I'll let you get back to it. Thank you for being with us.
Oh, thank you, Jess.
I'm going to throw it back over to Scott, and he's going to talk to some more of the teams to see how everything's going. Over to you, Scott.
Thank you, Jesse. Now, for those of us who are just tuning in, you are watching NASA's Moon to Mars Ice and Prospecting Challenge live, where university teams behind me are attempting to drill through lunar and Martian soil, simulated lunar and Martian soil, we don't have the real stuff here, to get to the ice that's hidden below it. Okay, this is very exciting, and this is not an easy task to do. How do I know this isn't easy? Well, I'm not doing it, that's why. But these teams do seem to have some very interesting solutions on how to solve this challenge. One day, systems like these could actually be used to extract water below the surface of the moon or Mars. And for future explorers, accessing water will be crucial for creating a sustained human presence beyond Earth. All right, everybody, I want to go over to the University of Houston and introduce everyone to my friend Charlene. Hi, Charlene. Can I just interrupt? How are you doing? So, how is everything going with your technology demonstration today?
Oh, we're doing fantastic. Things are working out pretty well. We had a little bit of issues at the beginning with our weight on the bit, but now that things are working out, just smooth sailing. So, yeah.
Okay, so I see it running over there. What's going on? How far down are you? Do you know?
Andrew, how far down are we?
We are 295 millimeters down.
Is that good? How much further do you have to go, or do you not know?
Looks like I have another 220 millimeters to go.
I think
Okay, so
we're
about
actually good.
halfway.
Well, thank you.
So tell me what you intend to do once you reach the ice below it. How do you intend to
true.
extract it?
Sure, so we're going to use a resistance
what?
heater
I'll take a
to
water.
melt the ice.
Yeah.
Then
Thank you.
after it melts, because it's going to melt radially, after it does that, we're going to pump it out using a peristaltic pump, and then it'll go through a filtration system and have clean water.
And is everything looking good so far?
Yes, everything is looking pretty good so far. We're actually really excited. Yeah.
Fantastic. Well, I wish you the best of luck. Get back to it. I hope for a spring of water to appear for you. I hope for a spring of water to appear.
Oh, okay, thanks.
Take care. All right, I'm going to throw it back to Jesse, who is with another team, and let's hear about another demonstration.
Thanks, Scott. I'm here with Dana from Stevens Institute of Technology. Thank you so much for being with us, Dana.
Yeah, no problem.
So tell me a little bit about your design.
So our design is back here at Deimos, and how it works is we have this rectangular frame, and there is the drill mounted on linear slides next to the extractor. So basically what happens is our drill slides over, goes down into the hole, and the drill mount that we have up there has a beam load cell on the top, and that measures our weight on bit and also creates our digital core by measuring the hardness that the impact the drill bit has. And then once it drills down, we have limit switches on the top and bottom that'll tell us when the drill has reached its final position and when it's up at the top. The drill bit will come out, and then it'll move over and the extractor will fall in and be lowered in. And then the extractor, there is a cartridge heater in the middle of it, and then a bunch of tubes surrounding that and little holes on the sides. So the way that we extract water is using a recirculation technique. So our pump will pull water all the way up through the extractor, and then once the extractor housing is filled, it'll push the water back into the hole, essentially melting more ice. And then we're able to pull all the water out at some point and push it through our filter, which is a gravity-fed filter made up of polishing pads and also a little bit of sand in between to help filter all that out. And then it'll go down to the collection bucket.
That sounds like you've put a lot of thought into this. Have you had any success so far?
Yeah, we actually have. We just drilled our second hole there, and right now we're in the hands-off mode. This morning we drilled our first hole. We started off hands-off, but we ran into an issue with our drill bit moving back a little too much, so we had to go hands-on and fix our extractor so it would fit in the hole. And we actually collected probably a little under a liter of water so far while being hands-on, which is really exciting. It's pretty clear, it's not mucky at all, so our filter is working really well, and we're feeling pretty good right now.
That is awesome. Have you been able to collect any information for the digital core yet?
We have, but we haven't really looked at it. I think we're going to focus on that a lot more tomorrow, so we have more time because we were working some of the kinks out of our system, but we can definitely tell because just our drill is a hammer drill bit, so it's really loud when it starts to hammer, and we can tell when it's reaching all the different layers.
That is awesome. I really wish you the best of luck. Thank you so much for talking with us, and good luck to you.
Thank you.
I'm going to throw it back over to Scott, and he's got one more team that we're going to talk to today. Over to you, Scott.
Thank you, Jesse. Okay, I want to introduce everyone to Team MIT and my friend Andrew. How you doing, Andrew?
Doing okay, how are you?
I'm doing great. So tell me about your design behind us here.
Sure. So our design, like many teams here, has two separate systems. We have one for drilling and one for heating. Our system is unique because we're trying to do radiative heating. So we actually don't let the heater touch the water directly. We heat it up to about 500 degrees Celsius, and it actually irradiates the ice around it. So since infrared radiation can penetrate water only to a certain depth, we heat like the outer shell of the hole and it grows on the inside. And we pick it up from the bottom.
So have you been able to reach the water yet?
We have. So we were able to reach water in less than an hour when in hands-on operations. We just tried to do a hands-off hole, which proved a little bit more difficult. So we're going to try and do another one here in a little bit.
So can you just explain for everyone at home the difference between hands-on and hands-off at this competition?
Sure. So for hands-on, you are allowed to physically touch the robot. You can feel certain motor drivers and you're like, is this motor getting too hot? Yes. Okay, stop it. For hands-off, you can't do that. You're supposed to have limited visibility and you can't touch it.
Okay, so how much water have you collected so far? Actually, if we look at these buckets over here, you can actually see you've gotten a bunch.
It's a big bucket. It's hard to tell exactly how much. So hands-on, we've got probably somewhere between a liter and a liter and a half, and hands-off, a few milliliters.
How much more are you expecting? Do you have any idea?
It would be nice to double or triple it before the end of the competition. We have about 2/3 of the amount of time left, so I don't see why not, especially if we're only getting better.
All right, well, hey, I wish you the best of luck, Andrew. Thank you very much. Cheers. All right, let's go find Jesse back out on the competition floor and see what is going on. Jesse, back to you.
Thanks, Scott. That was really cool to see all of those teams. It's so cool to see all the different designs coming together. Some of them are harvesting ice and melting it in separate chambers. Some of them are melting the ice directly beneath the soil, and others are actually letting the ice condense into a gas and then converting it back into water somewhere else in their system.
There are so many different ways to solve this challenge. It's really fascinating to see all the different ideas these students have come up with here. Okay, now NASA is not the only one to recognize the importance of technology demonstrations like the ones we're seeing here today. Industry sponsors do as well. So why don't we go and hear from one of those sponsors about why they chose to get involved in the Moon to Mars Ice and Prospecting Challenge. Jesse, I'm going to throw it back to you.
Thanks, Scott. I'm here with Rachel from Pancopia. Hi. Thank you so much for being with us.
Of course. Thank you for having us.
So tell me about your involvement in the challenge.
Okay, so Pancopia has been involved in the Mars Ice Challenge for several years. We sponsored their turbidity testing. So while most teams focus on their drills and getting water out, what we do is actually dealing with the water once it's out. So what we do is the water that's drilled out of the ice goes through testing to find out about quality measures. Usually it's just clarity at this point, but once we get more water, we can really see, how usable is this water? How easy is it to treat? What needs to be done to it in order to get it to a place where it can be useful to astronauts.
And why did they choose to get involved?
We chose to get involved mainly because we've been working with NASA since our inception as a company about 5 years ago. And the work we do for NASA is really about water quality in space. We've been working on a biological nitrogen removal system for the space station that helps them recycle water in space once it's up there. Don't think too hard about it. But water usability in space is really important because water is so heavy and it's so hard to get places, which is why the Mars Ice Challenges exist. Using resources that are available and already there to their maximum potential. So water quality is really important to us as a company, especially in space. So being able to sponsor this part of the Mars Ice Challenge is really perfect for us as a company.
That's awesome. I mean, it's such an important part of the challenge, making sure that the water is clear. So we're all grateful for your support.
Yeah, we love doing it.
Have you been able to see any of the designs here today?
Yes, I've walked around and looked at quite a few of the designs. They're really intriguing, and especially being able to see both the drills and the water that comes out of it throughout the years has been really fascinating, seeing how far everything's come along.
It's pretty cool that we've already seen a couple teams that collected water. So
I know.
It's
really exciting for us.
Yes. Well, thank you so much for being with us, Rachel. I really appreciate it.
Of course.
Back to the competition.
Thanks.
And I'm going to throw it back over to Scott and see how things are going out in the pit. Over to you, Scott.
Thank you, Jesse. And for those of us who are just joining, we are coming to you live from NASA's Moon to Mars Ice and Prospecting Challenge, where University of teams have gathered to attempt to solve a dilemma. How do you get through simulated Martian or lunar soil and find ice hidden beneath it? And then how do you extract that ice? It is not something that's easy, but these teams do seem to be up to the task. Okay, I want to introduce everybody to someone else, another NASA friend of mine who knows a thing or two about this challenge. Chris, it's good to see you again. How are you?
Good to see you, Scott. How you been?
I'm great. So I understand you know a little bit about this challenge, mainly because you helped put it together. So you're the best person to ask. What is the point of the Moon to Mars Ice and Prospecting Challenge?
Well, it's really all in the name there. We're learning how to do the things we need to do, both for our upcoming missions to the Moon and to Mars. We want to figure out how are we going to understand the subsurfaces that we encounter on the way to exploring both planets, or the planet and the Moon there, as well as understand how we're actually going to get at water to eventually enable us to do missions at Mars.
So we already know that there is water on the Moon and on Mars.
Yes, we found evidence that there's some amounts of water on the Moon, especially in some of the permanently shadowed regions of the craters there, and there's a lot of evidence for water on Mars pretty much all over the surface. So it's really a matter now of figuring out exactly how much there is, where to get it, and how to get it.
It's very exciting. Okay, so the students here today are attempting to solve a very difficult challenge. Can you tell me a little bit more about what they're doing and how differently each of them are approaching this?
Sure thing. So the way we're challenging them here is we've prepared these competition bins that you've probably already seen walking around that are filled with several different layers of materials that the student teams don't know about. We know what they are, but for them, we've only given them the most basic guidelines to prepare for. They've had to design their systems to drill through those and then get to ice that's at the bottom of the bins, extract that in some form, and convert it into clean water. Some of them are taking the approach of drilling in there. Others are trying to hammer their way in order to get to it. And then once they actually get their water and start pulling it out, they're experimenting with different ideas for how to filter it and get it clean enough that we would be able to actually use it.
So why do they want to filter it? Do they get different points if they do so?
Yes, so we give them points for producing cleaner water because cleaner water is what we're going to need, not just for the astronauts to be able to use, but also in order to make rocket fuel and propellant in order to come home. If we've got a lot of dirt or other materials mixed in with it, it's a lot harder to work with. So we're challenging them to come up with solutions to filter that water and have it as clean as possible.
What other ways can teams accrue points here at the challenge?
There's a number of ways. So in addition to the designs that you're seeing here today, these are all derived from designs they have made for the purposes of actually being able to fly at Mars. So in their papers that they have written with this, they describe how these concepts work on Mars and how they've adapted them then to the test environment we're showing today.
Oh, wow.
They've also put together posters to illustrate what they're doing, and they're producing what we call a digital core. This is where they have to use telemetry coming off of their systems in order to understand what those different layers are they're passing through, how thick they are, and how tough they are.
And how can those technologies one day help NASA?
Oh, they're going to enable us to do a lot of the goals we have for exploration. So right now, we've only ever landed a very few things both on the Moon and on Mars, and most of the knowledge we have about the surface only comes from the very top layers. But we're expecting that to get to some of the things we want to do, we're going to need to know how to get down deeper, and to know how we're going to do that, we need to be able to measure what's going on. So part of this is enabling us to better get the ground truth we need going down. The other part, the water part, is understanding how we're going to extract water to be able to use it someday.
So we've got 9 different university teams with anywhere from 5 to 6 or 7 people on a team. What are these students getting out of this, win or lose?
I think it's a ton. I think they're getting an opportunity to take on a real meaningful challenge that isn't just for their own educational benefit, but it's actually helping NASA. So in that way, they are helping carry us forward on this mission to the Moon and then on to Mars. In addition, they're getting the opportunity to interact with NASA engineers and folks in industry in order to kind of understand what they need and be able to take that back and inform them, all on top of getting to build and test some pretty cool hardware.
Yeah, I'd say. This is an awesome opportunity. Well, Chris, thank you very much for joining us today. And Jesse, I'm going to throw it back to you out there in the field.
Thanks, Scott. We are so excited to bring you live coverage from this year's Moon to Mars Ice and Prospecting Challenge, an important step in establishing a sustainable human presence on the Moon. Just imagine what the researchers of tomorrow are going to be able to accomplish when we make this next giant leap for humankind.
We have seen a lot of exciting prototypes today, Jesse.
We really have. We've seen some really cool ideas coming together, and they even got water.
They got water. We have water already. So these teams behind us, these university teams, have truly come up with some unique and out-of-the-box designs to solve this challenge. And these designs could one day help further NASA's human exploration goals back to the Moon.
If you want to learn more about NASA's return to the Moon in 2024, visit nasa.gov.
For the NASA's Moon to Mars Ice and Prospecting Challenge, I am Scott Bednar.
And I'm Jessie Wild. Thank you so much for being with us.
And remember, this is your space agency.
Get to know it.